Okay, wonderful. Well, I'm James Weaver. This is kind of bizarre, really, wearing headsets, and you all are wearing headsets, and when you walk into the session, everybody's real quiet. It's like there's no meeting happening. I did want to take a selfie with you. This is a weird selfie, right? Everybody's got headsets. We're all plugged into the matrix. And if you would do kind of a crazy pose, I don't know how you say that in Dutch, but please do a crazy pose. I'll get our picture together. Ready? 1, 2, 3, crazy pose. Awesome. I'm gonna tweet that right now here. So if you're not supposed to be here, then you should make up an excuse for why you're actually here, because everybody knows you're here now. So I work for Pivotal. We're a software company. We are the stewards of Java, our Spring, and Cloud Foundry, and we're a huge contributor to Apache Tomcat. Myself, I'm a developer advocate. I've written several books on Java, Java EE, Java FX. Most recent one is Raspberry Pi with Java. And I would like you to, if you're going to be in the neighborhood in California in next December, I would welcome you to attend our Spring One platform. It's a good time. The title of this talk is Machine Learning Exposed, and the way I learned machine learning was primarily by Andrew Ng teaching a Coursera course. So I wanted to give you an introduction, let him introduce this course to you, kind of introduce my talk and tell you a little bit about what machine learning is. By the way, I'm on Twitter at JavaFXpert, and I have tweeted these slides. So if you want to, you can actually follow along and run the demos that I run. So we'll go ahead and play this introduction here.
Dozens of times a day without even knowing it. Each time you do a web search on Google.
Start over.
What is machine learning? You probably use it dozens of times a day without even knowing it. Each time you do a web search on Google or Bing, that works so well because their machine learning software has figured out how to rank web pages. When Facebook or Apple's photo application recognizes your friends in your pictures, that's also machine learning. Each time you read your email and the spam filter saves you from having to wade through tons of spam, again, that's because your computer has learned to distinguish spam from non-spam email. So that's machine learning. It's a science of getting computers to learn without being explicitly programmed. One of the research projects that I'm working on is getting robots to tidy up the house. How do you go about doing that? Well, what you can do is have the robot watch you demonstrate the task and learn from that. The robot can then watch what objects you pick up and where to put them and try to do the same thing even when you aren't there. For me, one of the reasons I'm excited about this is the AI, or artificial intelligence problem. Building truly intelligent machines which can do just about anything that you or I can do. Many scientists think the best way to make progress on this is through learning algorithms called neural networks, which mimic how the human brain works, and I'll teach you about that too. In this class, you learn about machine learning and get to implement them yourself. I hope you sign up on our website and join us.
So one of the things he said was that machine learning is the science of getting computers to learn without being explicitly programmed. As developers, when we want the machine to learn something, we code that. When we want to perform something, we write that in code. But with machine learning, what you do is you train a model to learn. And so you're actually training the model, and then it learns something and then does something rather than you explicitly programming it to do that. So you see machine learning applications everywhere, for example, in self-driving cars, and the ability to tell what is in an image and even tell what's going on in an image. So not only recognizing things in an image, but then trying to pick out what action is occurring and then putting that into some language. So that's several levels of machine learning happening at the same time. So there are 3 types of machine learning. One is called supervised learning, And that's where you give it the right answers. So you typically feed it a data set, and the data set has features in it. Like, for example, in this data set, or in this example, we have housing prices. So we have only one feature, and that is the square meters of a house. And we have one output, which is the price in thousands of euros. So the machine learning application here, the challenge then is to be able to predict a house that you haven't seen yet. So we have a graph then that has the data points plotted for the information in the data set, and then we fit a curve or a straight line to try to fit that as well as we can. And then when we get a new house we haven't seen before, like 750 square meters, then we can say, we can predict that it's either 150,000 euros in case we trust the straight line estimate, or 200,000 euros if we put more stock in the curved estimate. It just depends on how we're fitting it. But we give it the right answers. We have this data set then that has all of those housing prices in it, and then we make predictions. And those predictions can be continuous values, and if it's a continuous value, we call that a regression problem. We could also classify things. So the right answer might be classes of things, and I'll show you an example of that. So then there's also, in addition to supervised learning, there's unsupervised learning. And that's where you don't give it the right answers. What you do is just feed it a bunch of data, and then you want the model to then make sense of the data. So one of the ways that it can make sense of data is to, for example, clustering. So you might have some marketing data or some social networking data, and you want it to find the clusters in there, maybe the market clusters. So that's an example of unsupervised learning. The third type of learning is reinforcement learning, and that's where you have an agent that you're trying to get it to learn to do some task, like play a game effectively, or maybe it's a robot and it's finding its way around a house. And reinforcement learning, you give it some reinforcement usually by giving it some points for completing a task correctly. And then its challenge is to be able to learn through that reinforcement. One of the success stories of that lately has been the Alphago project by Google Deepmind, Google Brain, sorry. It beat the world champion Go player in Go just about a year ago. So we're going to dive now into supervised learning. One of the classic data sets for data science and machine learning is the iris data set. It's a relatively small data set, about 150 rows, and it's got 4 features. Those features are the dimensions of an iris flower, the petal length and width, and the sepal length and width. And it's got one output, and that is a classification of which species it is. There are 3 species. So here's the data set, at least part of the data set. The features, again, those are the inputs, and then the labels are the outputs. So the challenge for the machine learning model is to be able to put separations, to find decision boundaries between the features. And that way it can make decisions when it's trying to classify a new one that it's never seen before. So this is a depiction of comparing those 4 features with each other on 4 different dimensions. If we had 100 features, then we would have 100 different dimensions that we're having to compare with each other. But each dimension, then, we're trying to find that decision boundary, And in this graphic here, we can see that it's a pretty clear decision boundary. As humans, we think pretty well in 2 or 3 dimensions, but when we get up to 4 or 100 dimensions, then it becomes more difficult. And so there are tools that help us reduce dimensionality and visualize that. So a very related discipline to machine learning, one that's very helpful, is called dimensionality reduction. And I'm sure you've heard of Tensor Flow in machine learning. Well, there's a visualization facility called Projector in Tensor Flow, and this particular visualization, there's a link here. It's at projector.tensorflow.org, and I'll go to that link, and we can see then these 4 dimensions of features visualized in a kind of a pseudo 3 dimensions. And you can see here the different species. There's Iris setosa, Iris versicolor, and Iris virginica. We can see that they're very clearly and very distinctly separate when we visualize that in 3 dimensions. So back in the late 80s, early 90s, the idea of doing machine learning or doing artificial intelligence by modeling the human brain was very popular. But there was a big problem in that Moore's law, where we have the computing power and storage and networking capability that allows us to do that, it really hadn't caught up yet. So there was an AI winter, a dead period for AI for several years. And then finally, because of how fast and how massively scaled, in terms of processing, cores, networking capabilities, storage capabilities to hold these large data sets, all of these things have really come together in the last 2 or 3 years. And now is a really good time to jump back into machine learning because it's for real now. And besides that, the academic researchers, it's a very hot topic. The academic researchers for machine learning are being sought after and paid like rock stars and sports figures. And so it's kind of a neat time to get back into machine learning. So modeling the brain, if the picture on the left is the brain as far as like the things in it, like neurons and synapses, and the inputs, the dendrites, and the outputs, the axons. Modeling that in an artificial neural network is over on the right that I'll blow up here. So to model the brain, we've got an input layer, and those are the features coming in. If we had the iris data set, we would have 4 inputs. And then on the output, we have the classification, if it's a classification problem. In this case, in the iris data set, it would be those species. And then in the middle, we have 1 or more hidden layers. That's why they call it a deep learning network. And each layer then has 1 or more neurons, and they're connected. Each neuron in one layer is connected to every other neuron in the adjacent layers. And so it's a fully connected network. So when I first started trying to learn machine learning and taking that course that I just showed you, I also, being a developer, I wanted to write an application that would help me understand what's really going on underneath. And remember, the title of this talk is Machine Learning Exposed. And so what I like to do with my audience then is to just pull away the covers and show you what's underneath. Not, and it's not that to use machine learning APIs you'll have to know all of that, but it really helps, and it gives you an intuition and a sense for what's going on underneath, so that you can more effectively perhaps tune things or be a more effective user of an API or develop your own machine learning facilities. So this application that I created uses models that came from Deep Learning for J. It's a Java library. And I built a facility and an Angular 2 front end that would allow me to visualize neural networks. So it's available on GitHub at this link. And again, these slides are available, so you don't have to copy down the link. Just go to the slide deck and click on the link. That's fine. It's got this Angular front end. And so I can click on the iris flower data set, for example. And watch when I clicked it, the numbers updated. And so what's happening there is the network is learning. It's learning how to tell when features come in. It's learning how to, through calculations, figure out what the right species is. And so I'm going to be going through those calculations. But another part of this visualization is the ability then to predict a flower you've not seen before. So, for example, if I found a flower, an iris flower, that the sepal length was 5 millimeters, millimeters, yes. Sepal length was, let's say, 3 millimeters. The petal length was 2 millimeters, and the petal width was maybe 2.5 millimeters. I hit predict, and the prediction then is that there's a 0.67 probability that that is an iris versicolor. And so that's how that works. In a classification problem, the last layer then typically gives you a probability distribution on which one it's likely to be. So the calculations, and I'm going to talk about how the neural network learns and how these numbers get here in the first place, but the calculation part where we do the prediction is actually quite simple. You have, on the left, you have some inputs, and to demonstrate this, I'm going to go to another example, and that is the XOR. This XOR is something that's known to all of you as developers. It's the exclusive OR, and so I've just modeled that in a neural network because it's a simple one that I can show you this calculation. So if I have true or XOR true, then I should get what? Correct, false. So I hit predict, and there is a 1 probability that it's false. So the calculation then is on this slide. We take the input, and then for each neuron in the network, in each layer, we do the following calculation. Step 1, we multiply the inputs by the weights. So in this particular case, if I'm trying to if I'm trying to do the prediction and I'm working on this neuron, I multiply 1 times 8.54 plus 0 times 8.55, and I get 8.54. And then I add the bias. Now the bias, these were the weights. Okay, the bias is this number here, and it's associated with a neuron. The weights are associated with the edges of that graph, the lines in the graph. So we add the bias, and then we get 4.55. And then each neuron you can think of as a neuron in the brain. And as you know, neurons in the brain, they have this ability to fire. So it's off, and then all of a sudden it's on. That's kind of the action of a neuron in the brain. So the artificial neural network mimics that. It's very much like that. And so it has a firing mechanism that typically looks like a curve. And so there's a sigmoid curve or some other kinds of curves that are expressed in terms of functions. So in this particular case, it's using a sigmoid activation function. So you take that 4.55 and you negate it, and then you plug it into this sigmoid activation function. So take the inverse of 1 plus e to the negative 455, and that comes to 0.99. So that's firing that neuron. And so you do that then with all the other nodes in the network. And the calculation is, it's a very simple calculation. It's a very lengthy calculation if you have lots of nodes in the network and lots of, hidden layers. But there are math libraries, scientific libraries, math libraries that do this very quickly. And it does lend itself to matrix and vector multiplication. So you can use a math library then to do this actually very quickly. And that's what the machine learning modeling packages use. So that's how we do the prediction. Now the hard part is training the neural network in the first place. So the way that happens, just kind of at a high level, is that you've got this brand new neural network that hasn't seen a data set yet, and you randomize, you randomly give weights and biases in the network, very low values, low random values. And then as you're loading the data in, you take a batch size, a batch of them, and then you run a feed-forward calculation, just like we did here. And you compare the result, what the neural network said that the answers are, to what the data set said the answers are. And because you've just given it random numbers, it's not going to be right the first time. So the challenge then is to adjust the weights and the biases in the network to where it'll be closer next time, and then closer the next time, until when you do the feed forward, that it matches or very closely matches what's in the data set. So that idea of doing that is called backpropagation. So you're minimizing what's called the cost function. The error in the network is the difference between what the data says it is and what you've calculated with feed forward. So that's called an error function or an objective function or cost function. So you're minimizing the cost function. And without getting into calculus or anything like that, I just wanted to give you an intuition for what happens in this backpropagation. So when you find the difference between, when you find that error in a given iteration, then you plot, internally you plot what the cost was. And then you decide, well, I'm going to, it's not perfect yet, I'm going to change the weights and biases in my network, and I'm going to calculate it again. And what you're trying to do is you're trying to bring this cost down. And so if I check it again after changing the weights and biases, I might notice that it has improved. And so then I know I'm going the right direction. And so as I'm updating the weights and biases, then I'm improving the situation, but then there's always going to be some type of minimum where you've converged or you've gotten as close as you can to converging on to where your model calculates the same as your data. You've minimized your cost. And so that's the sense of what's going on there. That's called gradient descent. And of course, if you have two features, then you're going to have two axes. And so this is what happens. If I'm adjusting two weights, for example, well, in a real neural network, you might have hundreds or thousands of them, and so you would have 100 or 1,000 dimensional graph that you're trying to graph, but where you're trying to minimize a very complex cost function. But the idea, though, is you're trying to descend the gradient and find a global minima. And so while you're doing that training, you have iterations that you're going through. Each iteration is you're going through what's called an epoch. An epoch is one complete pass through the data set. So in this particular model, Here we see around 500 iterations. We've minimized the score down to about 0.2, and then we've got this long tail here to where by 1,000, it's trained pretty well. This is actually on the iris data set. So this application that I created uses Angular 2. It's an HTML single-page client, and I'm using Spring, like Java and Spring, to make it really easy then to create a REST service, which I'm using for the prediction, and also to subscribe and connect and subscribe to a WebSocket, and then listen to that WebSocket for changes as the weights and biases are updated. So the Deep Learning for J library is at deeplearningforj.org, and then to get started with Spring, you just go to start.spring.io, and you can easily then pick what features you want in Spring, like REST service or a database or those kinds of things, and then it will help you create a POM for you, and then you can download that, and it gives you starter code as well. So it's incredibly easy to stand up those things. Sometimes I do this as a workshop, by the way. In this slide, there's a Tensor Flow Lab that it's actually quite a fun lab, and it's kind of it's TensorFlow in the browser kind of thing, and you're trying to minimize your cost. You're trying to actually have it identify data that's arranged in a circle, and you're trying to have it identify correctly the data on the outside and the data on the inside. So you're changing different hyperparameters, characteristics of your network, and then you're seeing how it affects this. And so it's a really good playground where you can get some good sense for tinkering with and tuning a network. And then here's a good blog post on just some ideas about optimizing a neural network. How do you know how many hidden layers to have, or how many neurons to have in a hidden layer? And it turns out it's as much of an art as it is a science, but that blog post does a good job of giving you a good sense of it. So there are various neural networks, various types of artificial neural networks. I just showed you a fully connected one, but there's also ones that are geared toward doing specific things. Like, for example, a convolutional network is typically used for image processing. So we have this image coming in, and we want to be able to then find out what it is. So this is there's a course at Stanford that on their homepage, it's kind of neat, the course homepage runs a neural network live in the browser, and hopefully we may see this. I'm not going to wait too long on it for it to start up here. But if you go to it sometime, it'll show you that it's putting different pictures up here, and then you can see the different layers and what it is recognizing, what it is seeing at the different layers as it tries to recognize an image, and then the output layer. So the architecture for a convolutional network is over on the right, it does use some fully connected layers, but on the left, it uses, we have this input of the image, which could be, thousands of pixels, and then it has a convolutional layer and a pooling layer. Convolutional layer does some filtering like Photoshop would, and it scans over the whole image and convolutes it, looking for edges or blur, does some blurring, things like that. And then the pooling layer then downsamples the image, because there could be thousands of pixels, and each pixel has, 3 features, and each of those features could have be a value 0 to 255. You want to be able to downsample that so that, and do that iteratively, by the way, multiple convolution layers, multiple pooling layers, to where when it gets to your fully connected layers, you've got a smaller set of neurons. So there's a really nice visualization that Adam Harley did, and it's at this link here, and it's called 2D visualization. So there's a link, and then you take the link to the bottom of the web page. The idea is that like when you do a handwritten digit on an envelope with, like in the US, the zip code, then a machine recognizes that rather than a person having to read all those. And so that's called the MNIST, M-N-I-S-T data set. So for example, let's say I drew the number 8. Then what we see in the network is the original image, and then we have a convolutional layer. And notice the lines that are going from the original image as we scan across the original image and then do a filter, a convolution on that. And we're looking for different things in these different images in the convolutional layer. And then this is simply a downsample where we would take maybe 4 pixels and downsample it to 1. And then we've got another convolutional layer, and then another downsampling, and then finally we have a fully connected layer. This layer is fully connected to all of the pixels and all of the images before it. Here we have another fully connected layer, and then here, I'll zoom into it. Here we have the prediction then on what that is. And so there's an interesting characteristic of this layer, this last layer. In this particular case, in this particular model, it's 100, it's held in a vector of 100 elements. A vector is like a one-dimensional array with 100 elements. In this case, it's a vector with 100 elements. Each element is considered a dimension because each element has a degree of freedom. So this image of this 8 can then be represented by this 100-dimensional vector of real numbers. And so that it can be used as a code for that particular image. So that brings me to the next idea. I'm going to skip past that one. That brings me back to the next idea, which is unsupervised learning. And this is, remember, unsupervised learning, you don't give it the correct answers. You try to, you give it data, and then you tell it to make sense of the data. So there's an experiment or a demo that Google did, Google AI experiments, called art. It takes art images from, hundreds of different galleries, art galleries. So it's got thousands of artworks from hundreds of different galleries, and typically when you would try to identify artworks and try to group them, you would tag them. You would give them some type of metadata about the artworks. Well, in this case, what they didn't tag them with anything. What they did was they wanted to visualize them solely based upon their visual characteristics. So, so this link is a demo to that. I'll go ahead and bring up the demo. And so somebody, after doing this visualization using an unsupervised learning technique, by the way, called T-SNE, T-S-N-E, somebody then looked at different things in this organization, in this image organization that this unsupervised learning technique created, and they picked out different things that were familiar. For example, they noticed that a particular area had ballet dancers. So we'll click on that, and then we see ballet dancers. Remember, they're not tagged. They're just using an unsupervised learning technique. And I'll use the 5 minutes I have left to tell you about that technique. So remember, in the convolutional network, that last layer was a 100-dimensional vector. of real numbers that represents an image. So what they did was, and I think they probably used 200 or 300 dimensional vectors, but you know, so far more than just 100 dimensions. But they took each artwork and ran it through what's called an autoencoder, but it came up with then a code. Let's just say it was a 200-dimensional vector for each artwork. And so if you have a 200-dimensional vector of real numbers, then you could put that in, you could imagine that in vector space. And similar to like the Pythagorean theorem, where if you just had, you know, 2 dimensions and you're saying the hypotenuse of a triangle is equal to the square of the hypotenuse is equal to the sum of the square of the 2 sides. If you're talking about 200-dimensional space, it's the same formula. It's called Euclidean Distance, where you take the sum of the square of all of the elements in the vector, and then you take the square root of that, and that is the Euclidean distance. And so what they did then was put them all in that vector space, use the T-SNE algorithm to then be able to reduce it down to 2 dimensions, and that's what we see here. That's why we can see things that are like each other in the same area. And I think, am I out of time, or do I have time for any questions? I have time for questions? Okay, I would like to entertain questions if I could. He's going to bring the microphone around.
Thank you. The examples you gave for output of neural nets are the same as, well, similar to the ones I've seen on the net, and they all seem to have a categorical output, classification output. Can you actually get a regression output as well out of a neural net? That's question number 1. And question number 2 was, can you use neural nets for reinforcement learning?
Okay, those are 2 very good questions. Okay, so here's an example of regression. So that's a continuous output. It's kind of a silly example because the inputs are actually numbers that we're going to add. So let's say we're going to add 1 plus, or 2 plus 1.2. I'll make a prediction, and then the output then is a continuous, yeah, so that's yes. As far as deep learning or using an artificial neural network with reinforcement learning, yes. The short answer is with reinforcement learning, typically we use something called Q-learning, which is a table of that holds states and actions that are that you're recording as it's going through, the agent is going through the task, and sometimes that table can get prohibitively large because maybe there's, you know, an infinite number of states that could happen. So you might use a learning neural network then to be a function approximator between, you know, between 2 of those things. So good questions. Other questions? Question here.
Thank you for the talk. Just one question. You are a very experienced software engineer, and you start looking more into this AI things, and you have this interest on it. But how do you see the testing on this part, like unit test into deep learning, integration test with these things? Because every time there is a new set of data, the code changes itself, so it learns. So how do you handle that?
Okay, so obviously, you know, there's no simple answer, right? But one of the techniques that's used in training a neural network is where you have training data and you have test data. So let's say with the iris data set, there's 150. It's a very small data set, 150. And so typically you would take maybe 100 of those and train the neural network with it. But then you would reserve 50 of it to then test to see how accurate it is. And there are several different ways of measuring accuracy. There's something called the F2 score, and there's there's false positives and measurements that have to do with false positives and false negatives and things like that. And because it is a big concern, right? Because you could have a beautifully trained data set, model from a data set, but there's something called overfitting, to where it could be trained too well, so well, that it doesn't generalize to something new that it's seen. So, and I think I'm out of time. Thank you very much for that question. Okay. I get to have another question. Yay. I mean, no, really, yay. I'll stay here all day.
Hello, thanks for the talk.
You're welcome.
I'm a bit concerned about the AI control problem. Do you think we'll find a solution to that?
Which AI control problem is that?
That AIs will become super intelligent and we'll have a Terminator scenario.
Right, yes, the uprising, the robot uprising. Well, I mean, you're already all wearing headsets and plugged into the matrix, so I think it's working, actually. Yeah, I think that cell phones, actually, mobile phones, actually, the only reason why we're still around, they let us live, is because they need us for mobility. They need us to be able to take them from place to place. Seriously, Andrew Ng, actually the guy that did the Coursera course, he tweeted, it's been a couple months now, because that same question was asked. It was like this big concern. And so his tweet was worrying about AI taking over is sort of like worrying about overpopulation on the moon, right? So it could someday be an issue, but we're not even near where we would need to be for that. We're still trying to get it to, like in the keynote this morning, recognize different images correctly. So, yeah, I'm not worried about real soon.
Yeah, we can have one more question.
Oh, one more question. Yay. Yes.
Hi.
Hi.
When you were talking about finding the convergence,
Yes.
That's a manual tweaking process, I would
Yes,
assume.
yes.
Would it theoretically be possible to train an AI to find a convergence for other AIs and thus use AI to train AIs?
Yeah, okay, so yes, that's, there are researchers right now trying to do that, using trying to observe training and have a model observe that, and then learning how to tune an artificial network. And this is a way off thing, is that you've all heard of quantum computing, with the qubits and all that, but there are some algorithms that are really good at very quickly doing certain optimization problems. And so I'm wondering whether perhaps algorithms like Shor's algorithm or Grove's algorithm in quantum computing space might lend itself at some point to that as well. Thanks for the great questions. Thanks for your attentiveness.